All right, so in this video, we're going to collect some data to determine the internal resistance of these DURACELL batteries here. I've got a suggested data table over here, and I've got an incomplete circuit sort of wired up. All I have right now is the voltmeter hooked up to the battery pack here, and you can see that it's about 2.7172 volts when there's no amps of current sort of going through it, right? Because the voltmeter, remember, has really high resistance if hardly any charge at all flow through it. So what we want to do now is wire up a variable resistor like this. Okay, this is a dimmer switch. You can see it's got a little slide there that can change like from bright to dark. So we're going to wire this up with an ammeter, and I'm going to use an analog ammeter. I like them a little bit better. I think it's cooler. Right there. Keep our data table in view. You can kind of see that, I suppose. And so now we want to go where? So we go out of the battery, and then this is just sort of parallel with it. So we'll go here, here. Not too bad. Maybe by so it's a little bit easier to read. All right. Out of the variable resistor into the ammeter, and then out of the ammeter back to reconnect it to the rest of the circuit. All right. So right now, let's just make sure. Oh, I got it wired. So you guys see how the needle is deflecting below zero? That's what time's done now. All right. So it looks like we've already lost some voltage in our battery there. It says like 3.7 or so. Okay. So if you want to stick with this, I mean, that was a valid data point, right? We saw it there, 2.720. But look right now, there's 0 amps of current, 2.7. So whatever, you want your EMF to be, remember the EMF is equal to the terminal PV when the current is 0. Think about the equation that we were sort of working with earlier. V equals E minus IR. Okay, so as we drive 0 amps of current through the battery, we lose no volts, right? The EMF equals the terminal PV. Now what we're going to do is we're going to vary the resistance here. So I'm going to change my dimmer switch. As I lessen the resistance, I will draw more charge from the EMF source. And so we should see sort of this needle sort of increase. And with a corresponding drop in voltage, right? As we drive more current through, this value becomes non-zero. and we subtract the lost volts away from this EMF. So this is the EMF right now. This is going to be where the data sort of intersects the y-axis, right? That's going to be the value that is the y-intercept. So now I'm going to increase the current by decreasing the resistance, and you can see that when the ammeter increases up to 1 milliamp, okay, we're set to the milliamp sort of range here. So there's 3 scales, 50 milliamps, 500 milliamps, and 5 amps. This is increased to 1 milliamp, and the voltage has dropped to 2.67. So we have another data point, 2.67 volts, 1 milliamp. So we can write this as just maybe 0.001 if you want to. All right, so we got another data point. This is in amps, right? And so we'll get our answer in ohms if we just sort of plot these small numbers. You can plot milliamps if you want to. You have to convert later. So we did that for the last time. All right, let me decrease the resistance further. And so now the current has increased all the way up to 0.002. And we find that the voltage has dropped to this. As I continue to decrease the resistance and therefore increase the current, we find a data point right there, 0.005 amps or 5 milliamps, and we can see a voltage of 2.64. Sorry, class, that should never happen. My wife too. All right, 2.64, 2.65. Let's continue to decrease the resistance, thereby increasing the current. And now we're going all the way up to so 11 milliamps, and we got 2.63. Okay, 11 milliamps. We got 1, 2, 3, 4, 5 data points. I know we like 7. I could try to go and fill in one of these. Like let's try to make the current somewhere between 5 and 11. So let's go to like 9. I can kind of use my judgment to see that this is, I guess it's exactly on 9. Sometimes you can say, like, even though the smallest division here is 1 milliamp, you can use your judgment to see it's kind of between 2 values. And so this one, you know, might be just under 9. So I could say, well, you know, maybe it's 0.0085. And even though it's not scaled sort of that precisely, me as a scientist sort of reading my instrument, I can use my judgment to say, you know what, that's exactly halfway between those 2 marks. And so that's allowed. So you can sort of use your judgment, but whenever you sort of use your judgment, anytime, I mean, I'm making a judgment about where that needle, you know, was when it read off that value, like did it perfectly line up with it? So every time we make a judgment, we're introducing uncertainty into our calculation. So here it's identical to this, right? It's 2.64. So like these 2 get the same coordinate. So when you go to plot it, your graph is going to look like kind of like, you know, that sort of. Or I should say that your data points will look like this. You know, like 2 of your data points are going to have the same exact y value, but that doesn't mean you connect the dots Okay, like I've done, you draw a single best fit line that represents the trend in the data. Remember that because the equation that sort of we mentioned a moment ago, terminal TD equals EMF minus IR, we can plot voltage against current, label our axes clearly, volts measured in volts, current measured in amps. And from this equation, we can rewrite it so it's Y equals MX plus B, where we already said that the EMF, okay, is going to be where the current is 0, right? So we already have sort of this value. And because this term here is equal to the slope, Y equals MX plus B, we know that by calculating the slope of our best fit line, when we plot this data, we'll be solving for the internal resistance of our DURACELL battery. And so here's the data that I'd like you all to sort of plot for fourth block, unless you've already started the analysis with the Energizer batteries.